happy to speak here. I thank organizers for giving me this slot. Good afternoon for us in Japan. I'm sorry that I couldn't attend physically in mid level, but I'm happy to attend online. So today I'm going to talk about multiply connected Fatou components, some for rational maps and some others for transcendental entire functions. So, well, it doesn't contain too much new things, but part for rational maps is not a very popular field. So with also advertisement, I want to start with some heuristics related to the multiply Fatou components. So this is my plan. So for rational maps, then transcendental entire functions, in that case, wandering domains, and some discussion which is related to Walter Bergweiler, Philippon, and Guinness-Strauss. Well, the most famous multiply Fatou components should be those for polynomials, the basin of infinity for disconnected Julia set. This is the case for quadratic polynomial, and this is for cubic polynomial, like z cubed plus a, some parameter a, where you have attracting fixed point somewhere. But let me pass to the more interesting example where you have Herman rings. So the famous Arnold Theorem guarantees that if you take a cubic rational map of this form, where, sorry, this should be less than 3, 1/3. Then for certain theta, if you adjust the rotation number to like Diophantine numbers, then the map, this map is degree 1 on the unit circle, and it is linear, real analytically linearizable. So that creates the Herman ring of period 1. I think when people talk about Herman ring, then usually they talk about this example that contains S1, because it's easy to look for the parameters. But then you can ask, are there any other type of Herman rings, for example, period more than 1? Okay, the answer is yes. So this was the question I asked very early in my career. And the answer is yes, you can construct by QC surgery. So here's the way you construct. So basically, for the simple type, which I explain in the next slide, simple construction is given by taking a Ziegler disk period P, and then like a multi-rational map, for a composition of P rational map. And suppose this composition has Ziegler disk, then you cut out Ziegler disk by invariant curves and glue them together. By surgery, you can create the Ziegler disk of period P. So at least at the beginning, this was not known, and this you can do. And with a search in parameter space of this type, the ones, I was able to find a parameter which is more or less like the Herman ring. I don't guarantee that this is Herman ring, but approximate parameter, which comes as a singular perturbation of z squared plus alpha, which has a Ziegler disk of period 2. And it's a singular perturbation that if beta and alpha is close to the critical point 0, both are close to the 0, then far from a 0, the map is almost like a z squared plus alpha, so close to the Ziegler disk map. And somehow you are introducing extra pole, then it gives a Herman ring like behavior. And the picture was created by the Ushiki a long time ago. So is this the only type of Herman rings? For example, for period 2. By only type, I mean looking at the configurations. For example, when you have the Herman ring, you can take an invariant curve, and you can orient the invariant curve in a consistent way, like a covariant way. So that means well, for this curve, everything else is like a right-hand side of this curve. If you go around this way in an invariant direction, it's the same for all of them. Okay, and well, this is in fact naturally simple, but the question is whether this is the only one. So it took me some time to realize that the other types are possible. So initially, at the beginning, I started that maybe period 1 is the only possibility. Then I realized that period 2 is possible. Then next, I consider that this type. So if you orient these ways, everything else is on the right-hand side of this curve. I thought this was the only type, but actually, there's another type, even for period 2, in the sense that if you orient in an invariant way, for this one, the other one is on the right-hand side, but for this one, the other one is the left-hand side. Okay, so this I call simple type, and this is called a non-simple type or configuration. And this one is also possible to realize, but it took some time to realize. So this configuration, suppose this is a sphere, and put the invariant curve this way with the invariant orientations, and you are permuting these curves. Period 2, you realize that if you take a curve joining two curves like this, then its image, this point, goes there, and then start to the right, and then you have to go to the other curve. So, and you have to come in from the left-hand side to this curve. So that means the image of this curve will go over there and coming back in here. So that necessarily creates a point here. So that this is also the inverse image of this invariant cycle, invariant curves. So somehow it is necessary to have this non-simple configuration. You need to have some invariant, the inverse images of this cycle. Okay. So if you realize this, it becomes possible to construct. One more thing to note is that, well, here you have an annulus. So suppose the inverse image of this curve is simple one like this, inverse image of this one is a simple curve like this. Then if the map from this domain is 1-to-1, onto this one, you have a problem because by Grotch inequality, you can't have an annulus and another annulus of degree 1. That means that they have the same modulus, but it's strictly smaller for this one. So that's impossible. So somehow a possibility is that you have a degree 2 from here to there, or degree 2 here to there, or other possibility that you have a critical point that the image may cover the bigger region. So after realizing this, you can just construct this non-simple configuration by this type of the surgery. But here you have a period of 2 cycles and inverse images. Now here I arranged so that this one maps here there by degree 2, and this one maps degree 2 to the other one. So there is an annulus in between, and this annulus is mapped to the bigger annulus by degree 2. So since you have a covering of degree 2, the Grotch inequality doesn't contradict for this configuration. So modulus here is 1/2 of the big modulus, and it's possible. So this way you can realize this configuration. So once you realize the configuration, you can realize. But here there was a discussion about the modulus, whether it is possible or not. Of course, it is possible to have a degree 1. Then you have to do something else inside. So somehow to realize this configuration, you have to go back to the inverse images and solve the problem of the modulus. So need to consider inverse images. So then you can ask questions. So I didn't mention, but well, one of the inequality I proved, like Kisaka mentioned, the Herman ring requires degree 3 for the rational map. So degree 2 rational map cannot have Herman rings. But for this particular configuration, so this one can be realized by degree 3 rational map like in a previous slide, the singular perturbation of degree 2 polynomial. But to realize this one, in fact, if you do this, you get the degree 4. So then the natural question is, well, instead of this example, can you find another example realizing this configuration so that the map is degree 3? And the answer is no. And well, you will need the degree at least 4 to realize this. So how can you prove such a statement? Because one possibility was kind of argued when you have a degree 1 here, well, this way. But there are other possibilities and so on. So how can you exclude? So in order to solve these problems, I would like to introduce the following notion. Okay. So let me stop about the Herman rings, but I'm continuing with Herman rings, but more general setting. So I take a map with Herman rings, and then there could be critical points landing on Herman rings. So you take the ground orbital critical points and closure and delete this from the set of Herman rings. Then the ground orbit, if you enter Herman rings, that will create the invariant curves. So you get a finite number of invariant curves inside Herman rings. So you get a finite collection of disjoint annuli. And when you take inverse images, if you avoid the critical orbit, you have a covering. So each connected component, again, you get the disjoint annuli. So at the end, what you get will be something like this. And these annuli are, well, isomorphic to the standard model, standard annulus model, concentric one. And concentric annulus is also, of course, foliated by concentric circles. So basically, you consider that the annuli are foliated by concentric circles whenever you're given these annuli. And well, this is not only for Herman rings, but whenever you have attracting basins, super attracting basins, the Ziegler disks, you can do the similar construction, starting from like an attracting cycle. If you take the linearizing coordinate, then in linearizing coordinate, you send the concentric circles to concentric circle, or for super attracting, you take a Boccia coordinate. Again, you have a concentric circle to go to concentric circle. The Ziegler disk, the same. Well, I can't deal with the parabolic basins, unfortunately, but still, for the rest of the types, you get this foliation by concentric circles, and then take inverse images just to delete forward orbit of ground orbit, closure of ground orbit of critical points. So you're avoiding critical values by deleting these. And again, connected components, you get this collection of disjoint annuli. So situation is, well, I drew only a finite number of them, but in reality, you always get infinitely many. And the situation would be something like this. So from these Herman rings or these objects, you're getting the collection of disjoint annuli, okay? With the natural foliation by circles. So basically, well, the Julia set is excluded from this foliation. So it's only a partial foliation. And well, in between you have a singular leaves with the critical points. So you get what you get is a partial and singular foliation, and concentric in the sense that the leaves are just like the concentric circles of the standard model. And the foliation is invariant under the dynamics. Okay, so this is what you get under Herman rings or other types, other than parabolic basins. And then from this object, I construct a pseudo metric, or the dxy. The value can take infinity, in fact, by the sum of all. So A is supposed to be a collection of disjoint annuli. And from this disjoint collection in the sphere, I construct a d of xy so that the sum over a annulus a in this collection calligraphic a, such that the modulus of a sub x and y, where a sub x y is defined like this. So suppose this is an annulus a, and the one x is in here, and the y is here. Then you consider all the leaves or circles that separate x and y. That gives you a partial annulus or maybe the empty set. So you just take the modulus of this partial annulus, or if it's empty, just to say it's 0, and take a sum over all annuli from this disjoint collection. So take the quotient by introducing inequality, the equivalence relation that the dxy is equal to 0 if and only if x and y are equivalent. Then what you get is essentially a tree was the metric introduced by this one. Remember that in this case, it's not really a complete metric in the sense that the value might take infinity, but still you consider that this is like a tree which have an infinity point. So with this one, it's obvious that if you are in the same leaf of this foliation, nobody else can separate the 2 points on this leaf. So the distance will be 0. So within this annulus, each leaf is identified. And essentially after the identification, you're going to get the segment. If you take the point in the complementary segment, everything in this component will be identified. So you create some kind of vertex. And this picture is with a finite number of annulus, but you can see that this annulus gives you a segment here. This gives you a segment here and so on. And if you have an annulus, this and that, this gives you the branching point because you have a segment here and segment here and segment here. And essentially, because of the Jordan curve theorem, what you get is tree. Because if you take a leaf, the circular leaf here, that separates the sphere into 2 components that correspond that a point in this segment will cut this quotient into 2 disjoint spaces. So that creates that you cannot have a loop in the tree in this set. So the quotient space is a tree. And in this stage, it's an infinite tree in general. And not only that, when you have a dynamics, since the foliation introduced by the Herman rings and Ziegler disk and so on is invariant under the dynamics, so the dynamics induces a map on this tree. And not only that, but the mapping of this tree is piecewise linear. And moreover, the Lipschitz constant, or I can say degree function or derivative is a positive integer. So this will be explained in next slide. So basically you get an object, the space, which is a tree, and another object, which is the mapping from T to T, which is piecewise linear with respect to the metric induced from this pseudo metric. And the derivative is a positive integer. Okay, so let's go to the next slide to see what is the derivative or local Lipschitz constant. And one more thing, that the Mostov point, because these annuli or the leaves are coming from the Herman ring or Ziegler disk or attracting basin, super attracting basin. So the Mostov points are eventually land on this one. For Herman rings, you get the segment, as I mentioned, that this is annulus with segment, or Ziegler disk, it's a one-sided infinite segment, which is periodic under the dynamics. For attracting basins, the attracting point is point at the infinity, and the return map is sending to the infinity. And it's a translation if it's the not super attracting, or if it's super attracting, again, the fixed point is at infinity. But if the local degree is k, it's like x goes to k times x, and it's a kind of escaping toward the point, infinite point corresponding to the periodic points in the center. Okay. So, next slide. What is the local Lipschitz constant? Well, so it's convenient to draw a part of the sphere and align this way. So sphere may look like this, or sphere may look like this. And I have a lot of annuli. In general, there could be infinitely many nested annuli. And for here, you're taking 2 points, then you're collecting all the leaves separating these 2 points, and that gives you the kind of distance on this quotient space. So it's like a segment. And if F maps this to the image, and the covering, well, for most of these annuli, the mapping is covering. And if the mapping is a covering of the same degree k, then each annulus, the modulus is multiplied by the k, modulus is multiplied by k. So everything in here will be multiplied by k. So that means distance is multiplied by same number. So in a sense, the distance is expanded by this factor k if the covering degree is k. Of course, in general, there could be some point in between so that the degree is different between for left-hand side and right-hand side. In that case, you have a discontinuity of the degree. But you can show that there are only a finite number of points with discontinuities. So let me go back to the problem I discussed. So for the degree of rational map realizing the Herman ring of period 2 of non-simple type. So the configuration was something like this. So from this configuration, if you extract a subtree from the annuli that separate these Herman rings or the curves of Herman rings, including this periodic part itself, you get a tree which is like a segment. Okay, because one tree is here, and one segment is periodic segment is here, another segment is here. Because of this orientation, if you draw a graph of the induced dynamics, periodic segment, because of this orientation convention that from inside to outside, from inside to outside, that correspond to these orientations, and that is preserved. So the mapping goes like this and goes like this. And the map will be piecewise linear, as I mentioned. So there could be some point like this with some folding point and so on. So look at how critical points are distributed. For example, here you have a folding point for the tree. So this segment and that segment is folded, and so that they are mapped to here. So that corresponds to the inverse images here. But what's the folding point on the tree in the original sphere? On original sphere, you have a curve, and another curve is mapped to the same curve, like here, corresponding to these two curves is mapped to some curve. And this annulus should be mapped to here. And the simplest, even in the simplest possibilities, you need 2 critical points to realize the mapping from annulus to a disk. So that requires the 2 critical points. And moreover, if we have a degree 2 on this side, or degree 1 here, degree 2 here, so total you need a degree 3, like a branch to cover. So that will require 1 plus 2, that is 3 critical points, the count of 3 critical points. So either you have degree 1 here, that means the piecewise linear map is slope 1, that requires 2 critical points, or you have a degree 2 or more, that requires 3 critical points. So start with degree 1, suppose. But well, you have to expand this smaller segment of the larger segment, and the derivative is always an integer. So somehow you could fold like this, that requires more critical points, but without folding, still you need to have, say, some sub-segment where the mapping has a slope 2 or more in absolute value. So that means somewhere you have a degree 1, and you have to switch to degree 2. And again, you have a discontinuity. What does it mean? So on the level of the sphere, so you have 2 points on both sides that correspond to these circles, and that maps to the image. So these 2 points map to some image, and degree 2 and degree 1, where you have a discontinuity. So to realize this, in fact, you have to have another inverse image, and that requires to have one critical, at least one critical point in here. Well, this is by Riemann-Froebis theorem, or realizing this as a branch to cover. So that counts 1 as a critical point. So in doing this argument on the tree, either you have 3 critical points or 2 critical points, and if you have only 2 critical points there, you have to have 1 critical point somewhere else. So doing both sides, you see that you need at least 6 critical points to realize. 6 critical points that it gives you at least a degree 4 rational map. Okay. So this is the argument you can show using the idea of this tree. Of course, you can do without a tree that you can consider all the inverse images and the modulus problem. But this modulus or Grotch inequality is essentially encoded in this tree and the piecewise linear map or the derivatives. Okay, this is a kind of simplest case to use this type of the object. Okay. Well, you can do this for period 3. For period 3, if you indicate the orientation of the invariant curves, so there are essentially 6 configurations up to this reversing the orientation of the invariant curves. And all this configuration can be realized, but this is the only type that can be realized by degree 3 rational map. These requires degree 4, these requires 5 and 6. But I just to show you the picture. The argument is very similar for this segment-like trees. And this type, you look at the inverse images on the tree, and degrees will give you the count of critical points. Okay. Well, this idea can be applied to other possibilities. One possibility is for the initial example for the polynomial with a disconnected Julia set. So if you take the basin of infinity using this Green's functions or the absolute value of a Botchov coordinate, you can just describe the basin of infinity like this. So the basin of infinity for this map has infinite connectivity, but near infinity, it's like this infinite cylinder with a point at infinity, which is fixed. So near there, it's a degree 2 mapping. But if you come back here at the level of a critical point, if you have a figure 8 shape for the level curve of the Green's function, and the image is a circle containing critical values. And then inverse images are just the copies of these. So there are two copies because there are two inverse images, 1-to-1. So you get something like this, and more inverse images, and so on. So you get the infinite branching figures. And well, it is obvious by definition that here, in the case of a basin of infinity or a super attracting fixed point, you foliate this basin by these level curves of virtual coordinate that gives you a segment. So altogether, what you get is something like a tree. It's a binary tree with a point at the infinity, which is fixed. Okay. So from here to there, you have a degree 2 or expanding that by degree 2. For the ones below, you have degree 1 mapping, which is isometry. So it's isometry from here to there, from here to to there. Okay. So that means this branch, this like a tripod picture, will be like a folded into this straight segment. So that corresponds to the critical point. So whenever you see this critical point, you are like a folding these, and this segment is mapped there, but these two are going to the same segment. Okay, this is the picture for the disconnected Julia set for polynomials. And so the Malk and McMullen introduced this one, and this is a special case of the tree I defined. Another one for the singular perturbation of the monomial map. It's called the McMullen map. For example, one simple case is z cubed plus epsilon over z cubed with small epsilon. In that case, well, I don't have Julia set pictures, but it's known that Julia set is a Cantor circle, like a Cantor set cross circle. And one way to see, not exactly this one, this middle picture is a bit different, but essentially the Julia set is like a Cantor set line corresponding to this nested circles. And most of the orbit outside the Julia set is escaping. So for example, domain here will come here, and then the domain near 0 will go to infinity, and the basin of infinity is fixed. Okay, so in this case, you can define the trees. Well, for example, here you have super attracting fixed points. So you're using virtual coordinate, you have a foliation by these level curves of virtual coordinate. And here it's the same. And here you have some critical points. So the foliation will be, will have a singularities. So the leaves are going like this, and another leaves are going there. And this one maps to 0. But for the inverse images, you have a similar ones with more eyes in the pictures. And if you consider the points, 2 points like this, you're taking only these annuli that separate. You're not taking these annuli because they don't separate. And this gives you the distance in here. So if you only consider a subtree from the circles that separate the 0 and infinity, you get the real line together with the 0 and infinity, or minus infinity and the plus infinity. Yes. And if you draw the graph, so this is a tree, and the graph will be something like this. So the infinity is a fixed point, and there it's like a expanding map with a fixed point at here. So expanding by a factor 3, like x goes to 3x, and the left-hand side is folded, and the critical points correspond to the here, and this part goes to the left-hand side, it's here, and then next you go to the right-hand side and escape to infinity. And so this is like a tento map, but this tip is sticking out of the box. Okay, so if you don't take these non-escaping point from the box, it's easy to see that you're getting this a Cantor set, 1/3 Cantor set inside, and this Cantor set exactly correspond to this Cantor set corresponding to the Julia set. So essentially, the dynamics and the J component is described by this non-escaping component, non-escaping set in this tent map picture. Okay, and in this case, it's a full shift. So you can analyze how they are like wandering, say, Julia component, say, etc. And well, you can say more starting from this picture or going back here. In this case, all the Julia components are circles, but and this is relevant. But you can put the extra branches of the tree and do some surgery to realize it. So for a circles, you take the critical values for wandering, say, circle, take critical values so that you can have a Julia component which have 3 components in the complementary regions. So you can realize any connectivity for the wandering J component starting from this picture and doing additional surgery. So this is a way you can understand and also create some more interesting dynamics. And well, as I mentioned, it's possible to go the backward construction under certain condition that you are given a tree with a piecewise linear map with some conditions, then you can go back to the rational map. To go back to the rational map, you need first the tree, like I mentioned, our tree, and you need a piecewise linear map with derivative, which are positive integers. And you have to have the dense orbit, which eventually land on the periodic segment corresponding to this. Oh, sorry, this is Herman ring. Ziegler disk and attracting basin or super attracting basins. And you have to add some information about these small spheres, like a mapping here, or mapping here, or mapping there, and so on. So this is like a small rational map, so that they themselves must be a rational map, a cycle of rational maps that specify what should be happening for this the resulting rational map. This I call the local model, so that represent these dynamics of branches and also the dynamics inside the small spheres. So now let me go quickly to the transcendental entire function. So there's pioneering work by Baker on a multiply connected Fatou component. So his first example was this type of infinite product. By adjusting the constant and RS, he was able to create the multiply connected Fatou component for this entire function. And later he proved that in fact this is a wandering domain as soon as you have multiply connected Fatou component. And there's also another example that the wandering domain has an infinite connectivity in the sense that taking each Fatou component and count the number of complementary component, and that is infinite for this other example. So the basic work Baker has done that whenever you have this multiply connected Fatou component, then you have the dynamics and U that must be escaping. So the mapping on the FU will go to infinity. And if you take a non-trivial loop for these multiply connected domains, well, this goes to infinity, and the winding number will be 0 for large n around the 0, well, or whatever finite point is. And in fact, after you iterate, the winding number actually tends to infinity, which was claimed by the Eremenko and Lyubich. Okay, this was learned from Kisaka. So Baker asked the question of, so does there exist the entire function of wandering domain with finite connectivity? So the infinite connectivity was already realized. So the question was the finite connectivity. And so I worked with Kisaka so that we can create doubly connected wandering domain. Okay. And the method we used was the QC surgery. And well, once you have a doubly connected domain, you can modify so that this inverse image has a finite connectivity, like three boundary component or any finite numbers. And the critical points eventually land. So for example, in this picture, to realize this, you need a critical point that land on doubly connected one. And in this case, you can also show that there's no asymptotic value, because there's the curve that is escaping to infinity with like a non-trivial winding numbers around 0. And this construction also answers to the Bergweiler's problem. So, well, the Kisaka talked about the inequalities about the Fatou cycles of Fatou component, and the key was to associate always the critical points for the rational case, or in general the singular values for the entire functions, or singular points for F inverse. And so the picture was simple for rational maps. So probably one wants to have the same picture for the entire functions. So are there any way you can connect the singular value for this wandering domain? And the example we constructed, in fact, you don't have a singular value that has an infinite orbit tending to infinity. In fact, with this example, each critical point is mapped to the critical value, and then next one is mapped to the fixed point, which we arrange so that it's a super attracting fixed point. So each critical point is a bounded orbit. So it's a negative answer to the Walter's question. Okay, so let me explain the construction quickly. So, well, I think I have motivated enough for you to how you use the tree for the rational map case. And this case for the entire function is even simpler, because if you want the doubly connected domains, that should, if you have these singular foliations for this annulus, in this case non-singular, you should be getting a segment. So you start with an R divided into segments, and the mapping on these segments. Well, this picture is a kind of misleading, because each time you have this segment, you want to have some map which is like a multiplication map by some degree, like a K1, K2, and so on. But if you do that, well, you overflow the pictures, so I'm cheating the pictures a little bit. So you take a segment corresponding to the annulus, and then the image should be a segment, and so also then the mapping between these one is expansion by degree K1, degree to K2, and degree K3, and so on. And these degrees should be going to infinity. And immediately you can realize that this should be realized by a cylinder. Instead of having cylinder or punctual plane, I just identify this with an infinite cylinder. And this concentric circle should give you this finite cylinder for each one. And for each one, you want to have a covering map. Okay. And then, of course, if the degree is different here, you have to kind of interpolate the dynamics in between. This is the idea of a quasi-conformal surgery. You make it a quasi-regular so that in general case, you have to introduce some inverse image of this curve. So inverse image of a curve like this would be two inverse images or more inverse images, and introduce a critical point to match the degree here and there. And you need several things to be careful. So in general, the principle is that the orbits that enter non-homomorphic region in, only finitely many times for the rational maps. But in this case, you allow the orbit to enter infinitely many times. But still, these discontinuities you interpolate, and the interpolation is very smooth as you go to infinity. So the dilatation is smaller and smaller. So even if you have an orbit going to infinity, the total dilatation is bounded. Okay, and then to ensure that this really corresponds to this doubly connected Fatou component, in between, we take some region that goes there and so on, that escape to infinity. So it's like a core of Fatou component, but there's intermediate regions. So this is a core and the intermediate regions. We arrange so that the critical point introduced in between will map to some point there. But at this point in the previous stage is mapped to this 0, which is fixed. Okay, so this way critical point does not enter to this the candidate core of a Fatou component, and from this you can conclude that the wandering domain is doubly connected. So I skipped the details because I'm running out of time. So the next is what in general the structure of a multiple connected wandering domains. And do you have a description like a tree I introduced? So the tree for or rational maps, I needed to have a singular foliation, invariant singular foliation to start with. We have a foliation like that, and what's the picture? And I was thinking about this, and actually I realized this Monday was a Guinness talk, or yesterday, and there was already a work by Walter Bergweiler, Phil Lippon, and Glenn Strala, and I think it covered more or less completely. But still, let me just reformulate what you can say. And I was going to explain in my view, but anyway, let me explain my view. So you can find the singular foliation on this multiply connected wandering domains with the invariant singular foliation such that each leaf, non-singular leaf is concentric circles in a standard annulus. And if you have a non-trivial loop in this multiply connected wandering domain, so in general, you may have these two different loops. They eventually goes to the same loop or multiple of the same loop in the further domains. So it has the same pictures. And if you try to identify the, so you take the multiply connected domain and look at its image and the orbits of 2 points and look at the hyperbolic distance of these 2 points. They tend to 0 if and only if the closure of these ground orbits coincide. So basically, if you have like a covering map, it's possible that by covering map, they actually goes to the same point. But the covering map of a higher degree, the inverse image is getting denser and denser on these leaves. And this is a true picture, even for the in general case. So for this relation, if you take the quotient of one domain, then it is a segment introduced by some distance relation I mentioned before. Then the singular foliation we can define can define the tree as I defined for the rational map. Then it is a tree and well, define the quotient space and which is a tree, and the induced dynamics is again the piecewise linear map whose derivative is a positive integer corresponding to the covering degree. Okay, well, it doesn't have to be corollary of this, but from these arguments, you can also conclude that with finite connectivity, eventually they mapped to the doubly connected wandering domain. So, well, you can look at the Bergweiler-Lippmann-Stallard paper, but I was going to present the view with the hyperbolic geometry using injective radius. But anyway, let me skip this part using color lemon and so on. Some color is mapped to another color by the dynamics. So it becomes a very simple question about the lifting of this mapping on the colors and so on. Okay. And then once you know that these trees can be defined, you can classify the possibility of multiply connected wandering domain. One possibility is that eventually doubly connected. And somewhere in the lower part, you can have a finite connectivity if you like. But the other possibility is that you have infinite connectivity, but there are two possible types. One is that you have like an annulus near the outer boundary, and then there are infinite connectivity, the complementary component. The other type 3, is that, well, near the outer boundary, you still have infinitely many complementary component, and inside you necessarily have an infinite the complementary component. So there are 3 types, and I say that you can realize all of them by the QC surgery. Well, this type I did with Kisaka, and well, it was obtained by arranging the position of a critical orbit carefully so that you don't interfere with wandering domains. But to create these two, you don't do that. So you, from here, critical point, you adjust so that you don't land on the same point as before. Maybe adjust the critical value more to the upper part of this core of the wandering domain or lower part of the wandering domain. So if you adjust the critical value to the upper part, you get the type 2, and to the lower part, each time you construct, well, it's not only one construction, but you have to do it infinitely many times, then you obtain this type 3 multiply connected wandering domain. So let me stop here. Thank you very much.
Thank you for this beautiful talk. Are there any questions for Mitsu first in the lecture room? Okay, perhaps online, some comments, questions.
Can I make one, David?
Sure, go ahead.
That's a wonderful talk, Mitsu. Thank you so much. That's absolutely brilliant. On the 5 theorems at the end, this is just a remark that our student, Gustavo Ferreira, who's there, has also studied this hyperbolic distance when it tends to 0. Well, just recently, he's interested in the fact that you get all 3 different types of behavior. You know, you get the tending to 0 in the situation you described, and also remaining fixed for some pairs, and decreasing but not tending to 0 for other pairs. So you get all 3 types of behavior within the same Fatou components. But it's kind of wonderful. It's one small bit of what you were talking about there. But
I see. So I think the 0 equal to 0 is a constant when you have 2 points on the same ground orbit.
yes, and they land on the same sort of level curve type things and go around, being dense there often. Yeah.
Okay, I see.
Yeah. But then you can get the other two types of behavior for the hyperbolic, the way the hyperbolic distance behaves can occur simultaneously for other pairs. Yeah.
I see.
Yeah. But so do you have a paper on this now?
No, but probably you don't need a paper if you have a student who have worked out already.
Well, this is just one small bit of what I mean, you have a big story here with the whole trees and so on. But,
Thank you.
I'd like to ask a question. Thanks for the talk, first of all. And my question, I think, actually overlaps with Phil's. I wanted to know if there's anything where we can find the details that you skipped about color lemmas and everything else.
The color lemma is, I think, a kind of well-known thing. And for example,
yes, but I wanted to know if there's anything where we can find all the all the lifts and the details that you skipped.
Reference I wanted to put was the Booza's book about the spectral of Riemann surface and so on, because it has a detailed hyperbolic metric calculations. And I quoted this theorem from his book. And the others are like probably Hubbard, the Doubly-Hubbard paper on this Thurston theorem has a smaller part that discusses about the coloring lemma. And I think in many hyperbolic geometry, on the paper and the Riemann surface that they uses, but I think this good introduction is in Peter Booza's book on. Well, I don't exactly know, but the spectra of the Riemann surfaces. The small color is not probably introduced there, but if you know the definition of injective radius, it's a kind of natural.
Thank you.
Continuation.
So, hi Mitsu, really nice talk
Hi.
and very inspiring.
Thank you.
I just would like to know, have you ever thought about Herman rings in the meromorphic setting? So when you have poles and you are much more similar to rational maps, but with infinite degree, whether the trees, this tree structure that you have could extend to that setting, the one that you described for rational maps?
Yes, I think as soon as you have this invariant foliation, especially when you have Herman rings, you can define. But the problem with meromorphic case is that the inverse image of an annulus can be an infinite strip. Yeah. In the case of rational map, since it's a finite degree, you have a disjoint collection of annuli. And as soon as you have an infinite strip as an inverse image, well, you have a problem to define the metric and so on. So you need a modification in a certain way to work it out. I think for example, some construction may be possible because if you ignore these inverse images, but I don't know if you can capture all these problems.
Well, I mean, the constructions are every configuration that you can show for rational maps is realizable for meromorphic. We proved this with John Peter some time ago, but it's nice to have this tree representation. Also, for example, to study the relationship with cycles and poles, which in rational maps, it's not important because poles, who cares? But in meromorphic maps, I believe that there must be some relation which is open for now. Nobody knows, right? And maybe this tree could help to do it if it was possible. Okay, thank you.
Yeah, I think for construction probably can be helped, but for general setting, this strip problem is annoying.
It's a problem, yeah. Okay, interesting. Thank you very much.
Thank you.
Are there any further questions or comments? If not, let's thank Mitsu again.
Thank you.
So now there will be, so tomorrow there will be a picture for the people